In this video, we shall take a walk through building and fitting a linear model, the complete exercise. So we'll start with the actual setup, construct a linear model, get the data, and understand how the linear model is constructed and how to fit it using R. So we shall start with our familiar example, the spring. Now the moment you get such a system, the first thing that you should always focus your attention on is to get hold of the box diagram, this box diagram. So treat it as a black box, carefully think about what are the inputs and what is the output. Don't forget the random error. I am not writing random error every time. So in this case, we have only one input, the weight, and just one output, this length. The input weight is a continuous variable and output is always assumed to be continuous. We have random error. So we expect this L, the output, to be a function of that input weight, the covariate, as well as of the random error. Now once we have this black box, the next thing that you should do is to take multiple copies of this object. In this case, it is the spring. Whatever system you are working on, if it is patient, you should take many patients. If it's spring, take many springs. But make sure that all the springs, all the patients, all the units that you are taking are as identical as possible, except for the inputs that you are going to consider. It is true that some amount of variation will be there, they will be considered part of this random error, but try to keep that as low as possible. So if you are working with springs, you now need to procure lots of springs which are as identical as possible. Do not use one steel string and another iron string, one spring which is long and another spring which is short, and things like that. So then you take hold of lots of different such springs and apply different inputs on them. So I have this situation. I have got lots of different springs and I am hanging different weights. So I am giving different inputs to the springs, and the springs are more or less identical. So whatever variability is inevitable comes because of the random error. So I have essentially identical springs. I am hanging some lightweight, so it is short, it is longer, and I am measuring for each of these cases the value of W, the input, and the value of L, the output. So remember, you should take multiple instances of this unit, and if you take n such instances, you are going to get n sets of measurement. In each set of measurement, you will get one value for each of the inputs and one value for the output. In this case, I have a covariate, so continuous input, continuous output. So once you have that, now you should write down the model. The model basically is the mathematical formulation of this black box. So that will look like this. So it is just a way of expressing the output L as a function of the input and the random error. So this is one way of doing it. I have taken L, that output, and expressed this as a linear function of this W plus the error epsilon. That is one way of doing it. So it is L equal to beta 1 plus beta 2 times W plus epsilon. Beta 1, beta 2 are unknown. Epsilon is the error. In our first formulation, we do not put any assumption on epsilon. We are going to put some assumptions later. They are Gaussian or whatever. Now this is for the black box itself. Remember, you have repeated this experiment n times. We showed all those springs. So we have got all those observations. So you must take that into account. So you will write the model now as Li equal to beta 1, then beta 2, Wi epsilon I. Notice that I represents that repeated trials. There is no I for beta 1, there is no I for beta 2. They are property of the spring. That is why we say that take springs that are as identical as possible. So the idea is this beta 1 and beta 2 is the common property of all the springs. So if they are made up of steel, all of them are made up of steel. If they have initial length, all of them have the same initial length. Try to do it as much as possible. Still there will be some variation which will club inside this epsilon I, and I runs from 1 to n. Now it is time to convert this model to the matrix form, which is pretty trivial. I just write it in this way. So I will write it as all my measurements L1 to Ln equal to, this is what is called the design matrix. Now remember, these weights W1 to Wn are designed by you. So you know what particular weights you have hung from the springs. So you know the exact value, you just know them. There is no randomness in them. So we have this thing, and I have written beta 1, beta 2. So just see that it is beta 1 times 1, beta 2 times W1, etc., plus all the errors. So Ishan asked the question, so how do I get those different errors? Now you understand. I am repeating this experiment every time. For each case, I am getting one line. So since I have repeated it n times, I have got n rows, and I have got two parameters here, two coefficients, beta 1 and beta 2. Hence, I have got two columns. Also observe that the first column of my design matrix is made up of ones. The second column consists of all the Wi's. So that is how you will do this in this particular example. So you got the form y equal to x beta plus epsilon. Here y consists of all these Li's. Okay, next let us see how we will represent the data. So we have collected our data. For each of those cases, n cases, we have got our Wi, which we know, which we have administered, and the Li's that we have measured. So we have got n pairs Wi, Li. Now we have to know how we represent the data inside the computer. So this is a crucial step, and I have seen some people who know linear model well, yet for a given problem they do not know how to express or how to store the data in the computer such that R or SPSS or SAS or any standard software can read them. Again, that box diagram will help. So this box diagram is of crucial importance. So I have the box diagram, and you can see that in the box diagram you have got this W, the input, and the L, that is output, and of course you have random error. Now, the way you have to lay out the file is like this. There should be two columns. There should be as many columns as there are arrows in this box diagram other than for the random error. So in this case I have got W, one input arrow, one output arrow. So there should be two columns in the data file. There should be no column for the random error which is not observed. So the way you should write it is like this. I have one input W, one output L. So I have written W and L, my what should I call my variables. So these are my variables. I have got W and I have got L, and I am writing down all the values of W that I have chosen. Suppose I hung 1 kg, then 1.5 kg, 2.0 kg. These are all uniformly spaced. They do not have to be uniformly spaced, but since they are under my control, the natural choice is making them uniformly spaced, and these are the measured quantities. Say these are measured in something like centimeters or something, whatever, all in some same common unit. So just observe how I have represented them. In this example it is pretty trivial, but for other examples it will be sometimes confusing. We will see such examples later. So understand how this layout is connected with this box diagram. Number of columns always equal to the number of arrows, including input and output, excluding the random error arrow. Number of rows always represents the total number of springs that you have taken. How many of such black boxes you have taken? It is always this. And you are writing for every trial of the experiment, the values are written as single row. One case, then another case, like that. Now when you want to represent this in a file, typically in a text file, I would suggest that you just store it directly, give the headings L and the two sets of values. And this is ready for ingestion in any standard software like R or SPSS or SAS, whatever. So this should be the format. Always you should be able to write down the black box first, and the black box should dictate how your data layout should be. So now I am going to show how you represent the data in a file. I have already mentioned how you lay the data out. So here is an example. I have given you some data, 1.0, 1.5, the same data that I showed. There is one major difference between what I showed in the last screen and what I am showing now. Namely, I have put lots of commas. This is called the comma separated value format. So I will just write that down for you. Comma separated values, abbreviated to CSV. The CSV format is very useful for data interchange between different softwares. It is very easy to type, and it is very easy to get CSV formatted data from other sources. Like if you have an Excel file, you can export it as a CSV file. So this is a CSV file. As the name suggests, the name is spring.csv. So it is a CSV file where I have written one case per line. So this is one case, 1.0, 5.29, 1.5, 6.31, etc. There are as many cases, that is as many lines, as I have trials of my experiment. So I took these many observations. Also notice that in the very first row I have written the names of the variables, and I have used more descriptive names than merely W and L. I have called them weight and length. So this is how you should prepare the file. There is no comma at the end of the lines. There are commas only to separate the different numbers in the same line. It is not at all important that you write them one on top of another. You might as well make it what is called a free format thing. So you can put spaces. That is not a problem. What you must not do is something like this. Then it will be confused. It will think that there is nothing here and 5.29 is standing on its own. It will give you error message. So we just need to have equal number of numbers per line. Okay. So now I have started R here. So I need to read the data. Now when you read the data, you must understand that R always has a concept of working directory. Whenever you try to read anything from your hard drive, R will look for it by default in a certain directory or folder, which you can get by the command getwd, get working directory, which in this case happens to be this long thing. When you start R, the default working directory will be possibly something which is your home directory or something like that. So you need to tell R to get to that correct working directory. Depending on how conversant you are with the computer system that you are using, it might be easy for you, it might be very difficult for you. You just have to figure that out on your own. So you can use the command set working directory and then write down within quotation whatever working directory you want it to be. It could be like C, then slash, users and your name. It could be something else. So you just have to figure out. Make sure that your file, that spring.csv, is also in the same folder. The most common problem that I hear from students is that my R cannot find my dataset. I have my dataset here, R cannot load it. Mainly the reason is you have kept it in one folder and R is looking for it in a different folder. Or conversely, what you can do is that, not conversely, alternatively what you can do is that when you try to load the file, specify the entire path. So I will start loading it. Give it a name. I will call it dat, for want of a better name. Read.csv, that is the way you read a CSV file. In my case, it is already in my working directory, so I will just give the name spring.csv. And incidentally, if you have problem with this, then please tell me during the class, and you can share your screen so that I can see what is going wrong. That is fine. It is quite a natural problem for a beginner not to be able to load the file. So I write this. When you load any data set, make sure that you have loaded the correct thing. The first thing that I will do is dim dat to check if the size is okay. It says 62, 1, 2, 3, 4, 5, 6. Remember, there are 7 lines, but the first thing is heading, so this is not counted. 2 columns, fine. This is a very small data set, so it's a good idea to print the entire data set and convince yourself that that is indeed what you have. If you have a larger data set, you will print only the first few rows and the last few rows. And the names can also be seen, their weight and length. So I have my data set. Now I want to fit my linear model. So one technique is directly to write down that entire X matrix, but we will not do that. We shall be clever. I will create a new variable which I call fit. And then I will write LM, you already know that stands for linear model. Now I will have to write down the measurement vector. In my case, this is length, so I write length, tilde, that is the approximate equality sign. Now what I plan to write after that is where the strange thing will happen. I will just write weight. So if I just write weight, it will understand it, except that I need to specify data equal to dat. Or I might just write dat, that will also do dat. Oops, dat. Let's understand what it means. It means that I am working with a data set stored in dat, and I am trying to fit a linear model to length in terms of the variable weight. We already know that R has the habit of appending a column of ones. This is going to help us here because we know that intercept column 1, 1, 1, 1, 1, we do not have to apply it ourselves. So just hit enter. R does not say anything, and you know for R, no news is good news. So it has done it. Just to make sure that R is really working with the design matrix that we want, just check model.matrix of fit, and you will see indeed the first column is 1, 1, 1, 1, second is 1.0, 1.5, etc. We call them beta 1 and beta 2. R calls the first one intercept, the second one weight. So this weight is basically the coefficient of weight that it's trying to compute. Okay, so let's try to look at what is inside fit. I will type fit, and I get the coefficients. So the least square estimate, beta 1 hat, the intercept happens to be 3.283, and beta 2, it says weight, it is the coefficient of weight. So it should not really say weight, it is the coefficient of weight, 2.010. So that is the unique least square estimate. How do I understand it is unique? Because I do not see any NA. If at least one of the coefficients is reported to be NA, I will understand that that is only one possible least square solution and it is not unique. In this case, it is unique and we have got it. Now when you do that, you get the least square solution, you must make sure that it is a good thing. So I should do something that I should have done at the very beginning. I should really not start to fit a linear model before I make a plot. I should have made a plot. Stupid me, why did I not make a plot? I should have always done a plot first. So I will just replay my command, plot, length versus weight. Whatever you are writing before the tilde is your y variable, and whatever comes after that is your x variable, and it's not called plot, it's called plot. and you get this. Whoa, this is just straight line. So there is some amount of random variation, but you hardly see that. So this is very good. It just looks very, very, very nice fit. So yes, linear model in this case is a good fit, so you can really rely on the values. You can now try to play with it. You can try lines, and I will try fit. Oh, I should show you what's inside the fit variable. Try names fit. And fit has many things. Fit has got coefficients, it has got residuals, something called effect. You understand what is meant by rank of the design matrix. Fitted values, that's useful. Assign, I do not know what that is yet. QR, I do not know what that is. DF residual, wow, and some other things. So let's try certain things. Fit $coef. I have abbreviated coefficients to coef. You can abbreviate as long as you do not run into any ambiguity. And these are the coefficients that you already saw. I can try to see fit $receipt or res. These are my residual vectors, that is y minus y hat, that perpendicular vector that I drew earlier. And what else? Okay, try fit $fitted values. Fit $fit. So this fit is an abbreviation for this thing, fitted values. Fit $fit. This is your y hat, that is the foot of the perpendicular. And try rank, fit $rank, rank of the design matrix x. In this case it is 1, 1, 1, and all those xi's, since not the xi's, the wi's. Since the wi's were not all same, so the rank of this matrix is 2. It is just reporting that 2. Okay, now what do you really typically want to do here? You would like to show the straight line on top of it. So let's just try to do that. I will say lines. Lines will do it, and then I will write fit $coef. And let's take a look at the plot. Oh, I do not see the plot. What happened? I do not know. Okay, so it will not do that easily. Lines $fit will do it. Oops, no. I am doing stupid things, so I have to write separately. So there was a smarter way of doing it. Can't recall. So fit $coef. The first entry. Remember, coef is a vector of two things. The first is the intercept, and the second is the slope. Now, oh, I remember the mistake that I did. I remember. I should call AB line. Fit $coef. Yes, that's the thing. I forgot. And now it has given you the line. And you can see it is a very good fit. And that brings us to the end of this video. Now I will just highlight the main steps, because these steps are extremely important for any kind of linear model. The important steps are, number 1, you should draw the black box. You should always start by drawing the black box. That will make it clear what unit or what system you were talking about, if it is a plot or a patient or whatever, and what are the inputs and what are the outputs. Then you take n sets of measurements. So whatever is your system, you take n copies of that. Maybe you use the same thing n times, and you take measurements. And remember, you are measuring all the inputs and the output every time. Then you create a CSV file with all those things. If your box is like this, k inputs and 1 output, there are k input columns, 1 output column, so there are k plus 1 columns in your file, and n rows in your file, excluding the very top line, which gives you all the names. And I would always suggest that you make it a CSV file. That means that you separate them with commas. They will make your life a lot easier. So make a comma separated file, and there are n many such lines. Then you load this file in R, dat equal to read.csv, whatever is the name of your file. put it inside quotation marks. Then you should check the sanity of the data set, that is whether you have really read the right thing, check the names, whether the same columns as you have wanted, the appropriate number n and the appropriate number of columns, look at a few first observations, etc. Whenever you load a data set, check the sanity of that. Then you should plot out against the different inputs. It just depends on the particular problem, which plot you think is meaningful. Try to explore. There is no hard and fast rule for that. Try to make box and whisker plots, try to make scatter plots, etc. We shall see more examples of this later. Then you actually carry out the fit. You can use whatever variable name you want. I am using fit equal to lm out, then tilde. In this ... you have to write whatever appropriate model you try to fit. In our case, we just fitted linear regression, so we just wrote the name of the input. We shall see more variants of that. Then write comma dat, that is the name of the data set that you have used. This name is optional. You can use some other name also, just make sure this is same as this name. Once you get the fit, you should explore that, look at what are the estimated coefficients, etc. There are various ways of exploring. We have seen basically a few. We have seen how to find the coefficient, the residual, the fitted value, etc. Finally, and this is of crucial importance, you should assess the goodness of fit. Just because you have applied least squares method does not mean that the model is a good fit. It gives you the best possible thing, but if the model itself is very bad, then even the best estimated coefficients will not save the day. So you should assess the goodness. The simplest technique is to plot the fitted value with the original output thing, or just as we did, we just took the scatter plot and drew the line on top of that. There are lots of different ways by which you can assess goodness, but remember that you must do that. If you are happy, fine, your analysis is over. In practice, most of the time you will not be happy with the goodness of the very first fit that you get. In that case, you will go back to step 7, you will tweak this thing and again keep on doing 7, 8, 9 repeatedly until you are finally satisfied. So make sure you understand this workflow clearly, because we will be doing this again and again all throughout this course.